As we continue our discussion of the least square regression line, we are going to answer two questions. First of all, is a linear model appropriate? Secondly, how good is our model that we've come up with? We know that all models are wrong, but some are useful. So how useful is it? So to determine if a linear model is appropriate, there are two things you need to check. First of all, you want to look at a scatter plot always. It's really easy to toss it in the graphing calculator and examine your explanatory versus your response variable, and we better be seeing something that is somewhat linear. If we have a curved pattern, we'll look at ways that we can possibly straighten it later on. You also need to check the residual plot, which should show random scatter with no leftover pattern. Really specifically, if you see a curve or you see something that we call fanning, your residual plot is showing you that your model is not appropriate. Okay, so on the screen here, you are being shown your least square regression line, okay? And we know now that the residual is the difference between your actual y value and the predicted y value. So here we have a negative residual, again looking at the data for the Ford F-150s. And in a least square regression model, the sum of these residuals would be equal to 0. You have, of course, some below, some above, so if we have a good fit and it truly is a least square regression line, it will sum to 0. Occasionally, when you're using technology, it may not quite be 0 because of some rounding issues. Now, when we actually find the least square regression line, what it's doing is it's finding the sum of the squared residuals, and this gives you a nice graphic for it. So if this segment here is your residual, that value squared, well, would be is equal to the area of this square. So if we are reducing the sum of these squares, that area, we are getting if we're minimizing it, we're getting the sum of the squares of the residuals. Okay, that's in general. So what is a residual plot? Well, here is an example where we have all of our residual values calculated, and here they are. For each of the truck values, our actual minus our predicted, here is our initial scatter plot. And what a residual plot does is it kind of magnifies the deviations of each of the points from the line. So you could think of this here as being your least square regression line. It is also the mean of the residuals. It's equal to 0. Because if the sum of the residuals is 0, then the mean is 0 as well. But you can think of this as your least square regression line. So it magnifies the difference between each of your point values. So just to make sure you're with me, if I pick out a specific point in my original scatter plot, which that one right there, which is like 70,000 or so, where does that correspond over here? Well, it was underneath at 65,000 again. It's this point right there. Okay. So again, what are we looking for? We're looking for random scatter, and I would say that in my scatter plot of my residuals, or which is known as a residual plot, I'm seeing random scatter. There's about an equal amount of points above the regression line, or the mean of the residuals, which is 0, as there are below. I don't see any leftover curved pattern, and I don't see any what we call fanning, which I'll show you what that looks like in a second. I am going to show you how to do this on the graphing calculator. When you calculate the least square regression line on your calculator, it's automatically stored in the background of the calculator after you've run StatCalc option 8. And when you go into StatPlot, I have my data, my X is in L1, and I'm going to change my Y list to say residual. And I'll actually show you that now with a quick video. Let's look at how to graph a residual plot and a reminder on running your regression equation. So in Edit, I have stored my L1 and L2 as the data on the Ford F-150 trucks. I'm going to run my regression, my least square regression line by doing stat calc option 8. And I'm going to tell the calculator that my data is in L1 and L2, and I would like to store my regression equation in Y1. So I go vars, yvars, select function, and Y1 is the first one. Go down to calculate. Here's my y-intercept, my slope, my coefficient of determination, and my correlation coefficient. I should quickly look at my scatter plot, but you will see if I just hit y equals, it has copied and pasted my regression equation into y1. So in stat plot, I make sure I can see plot 1 is turned on using L1 and L2, and it's set to scatter plot. So if I hit zoom 9, here is my scatter plot with the least square regression line drawn. So my correlation coefficient, which was like negative 0.81, is confirming that I have a fairly strong, moderately strong negative linear association between the miles driven and the selling price of the Ford F-150. Okay, now the residuals are automatically stored already. Whenever you run the regression feature on your calculator, it automatically stores your residuals into a list called residuals. If you run another regression, that new list will be stored. So it's always storing your very last list. So if I go into edit and I want to see my residuals, I'm going to enter them into L3 just because I want to see what they look like. So if I hit L3, I'm going to hit equals, and I want it to equal my residuals. So I'm going to do stat, or not stat, I'm sorry, second stat to get list. And you can see here are my lists, and option 7, resid, stands for residuals. So I'm telling the calculator I want L3 to equal the residuals. So if I hit enter, here it automatically fills in the difference. This right here, L2, was the observed or the actual price, and it's subtracting the predicted price to get this negative 4,764, which would tell me that my actual price is that much under that predicted by the model. So in this scenario, for this point, the model is over predicting. Okay, so here are all 18 residuals, and I can look at my residual plot. So I'm going to go to stat plot again. I'm going to just change this now. I'm going to keep my X values as list 1, but my Y values I want to change to residuals. So I need to choose my list, so second stat. I can do one of two things. I already put them into list 3, but out of habit, I just choose 7, the residuals. And zoom 9. And here are my residuals. And you can see that fairly even scatter. I don't see any leftover patterns, any curves, or any fanning. So I would say that it's a good indication that we have that our linear model, the least square regression line, is appropriate. And we, of course, will talk about the standard deviation of the residuals and R squared to see how good is our model.
So what does a good residual plot look like? Well, it's going to be like this. And just to label this, 0 is the least square regression line, or the mean of the residuals. Your positive residuals are here, your negative residuals are down here, and X is your explanatory variable. Okay, so a good one has points kind of equally above and below with no leftover pattern. So a definite bad residual would be if you see a very clear curve, this is telling you your model is not appropriate. Something else that you may see more of is, at first it's looking pretty good with about an equal amount above and below, and then all of a sudden your scatter plot kind of takes on, it has much more variability. There's almost like we call it a fanning pattern, goes out like this. That would be a bad residual plot as well. So I would encourage you right now to pause the lesson and go and do the Khan Academy practice that I've assigned to your class, where you're just identifying some things about residual plots to make sure that you can read them. As soon as you're done, come back and finish this and we'll talk about standard deviation. So when we're looking at how good is our model, one of the things that we're going to compute is the standard deviation of the residuals. So the standard deviation is going to estimate the typical prediction error when using your least square regression line. So the actual formula is given for you on the AP formula sheet. It is this one right here. It's under standard error of a sample statistic. And you can see it is finding the sum of the squares of the residual. You're actually dividing by n minus 2, and I'm just going to kind of say, trust me, we'll learn about why it's n minus 2, not n minus 1 later on in this course, and then it's the square root of those is going to be the standard deviation of the residuals. And what it does is it gives the approximate size of a typical prediction error, okay? So again, I'm saying that S is defined as the sum of the residual squared over n minus 2, and you take the square root of that. When you are asked to interpret it on anything in this course, here is kind of a general statement that you want to include. We'll say the actual, and then you put your y in context, is typically about S units away from the predicted number by the least square regression line. So on your graphing calculator, to find the standard deviation of the residuals, because you're not going to want to do this by hand, the easiest thing to do is, just like I showed you in the video, store your residuals in one of your lists. So I chose L3. And then you're going to run your one variable stats on that list. So here is a screenshot of my one variable stats. Now you can't just pick off this regular standard deviation because for a sample that's using n minus 1. So what you're going to need to do is you have your general formula, it's the sum of the squares of the residuals in the numerator. So a little bit of computation by hand. This would be, the sum of my x squares, the sum of the squares of the residuals is this large number here, divided by n minus 2, and since n is 16, it would be divided by 14, and then we take the square root of that. So when you toss that in your calculator, I get approximately $5,740. So my prediction is already, I typed it on the screen to speed things up a little bit. I would say that the actual price, so I'm putting the y in context, the actual price of the F-150 is typically about, now I state my standard deviation, my S value is typically about $5,740. It's got units away from the price predicted by the least square regression line. So just think about for a second, if it's a good model, would you want a high S value, lots of variability, or would you want a low S value? Now we're going to look at R squared, which is abbreviated sometimes as this R-SQ in computer outputs. On your graphing calculator, it will be listed as R squared. And yes, it is just taking our correlation coefficient and squaring it, but it actually is explaining something much more important on our model. When you're interpreting it, I'm going to give you kind of a blanket statement, and then I'm going to do my best to explain what this means. You're going to use this blanket statement that you're going to take your R squared value and say about R squared % of the variability in your Y. put that in context, is accounted for by the least square regression line, or you'll have the ending say something like, is accounted for by the variation in the x in context. So it's what amount of differences or variability in your y's is actually being explained by that explanatory variable. It is never, you'll see statements like the percentage of points that your least square regression line goes through. Never true. I'm going to try to explain this to you. Here is the formula, though, for calculating r squared. I won't make you calculate this by hand when the graphing calculator does it for you. I've only ever seen it where you have to explain what it means. Here is your actual definition, okay, and it is, of course, your coefficient of determination. It's a fraction of the variation in the values of y that is accounted for by the least square regression line of y on x. And here's your formula. So I'm going to use the truck example to try to explain r squared to you. So suppose that we randomly selected an additional used Ford F-150 that was on sale. What should we predict for its price? And this is our scatter plot, but I've added a new horizontal line. This is our mean y value, so the average of all the y's, okay? So if you didn't know the number of miles on the truck and we wouldn't be able to use the regression line to make a prediction. So what should we do? Well, probably what most people would do is they say, well, what is the average price the truck is selling for? This y value, okay? Interestingly, if we did the x value, there'd be a vertical line right here, and the point x bar, y bar always falls on your regression line. Okay, but anyway, back to what I was stating. How much better does the regression line do at predicting prices than simply using the average price of all 16 trucks? Well, how much better it does is this value known as r squared, okay? So we want a high r squared value if it's a good model. So a low standard deviation of the residuals, but a high r squared. So from my graphing calculator, I saw an r squared of 0.66. So I interpret this as, I say, about 66% of the variability in the price of a Ford F-150 is accounted for by the least squares regression line with X miles driven. Well, what about the missing 34%? Well, the variability in the prices, so sometimes you're a little bit above your least square regression line, sometimes you're a little bit below. Well, that's what's being explained, that variability by the regression line with X miles driven. But the other 34% that's unaccounted for, well, could be other things affecting the price of these trucks, like the color of your truck, the age of the truck, the condition of it. If it's got a dent in the side, there are other things other than just the truck's mileage that can be explaining the variation in price. So just to pull it all back together, your stronger models are going to have a low standard deviation of your residuals. Remember, your residual is your vertical distance, so there is not much difference here. The low residual and a high r squared. Okay, so that means most of the variability in your y's, if it has a high r squared, is being explained by the explanatory variable. If you have a weaker model, you're going to have a higher s value and a lower r squared. So high S means, you have more typical distance in your residuals, you've got greater vertical distances between the least square regression line, and then a low r squared value. So your regression model is not explaining as much of the variability in your y's. Okay.